The electrical code addresses various grounding configurations, but the specifics of a delta ground, and whether it's mandated after a certain amperage threshold of service, is not explicitly stated within the provided text. Delta systems, known for their three-phase power delivery without a neutral conductor in their most basic form, require careful consideration for grounding to ensure safety and proper operation. There are generally three types of delta systems one might encounter: ungrounded delta, corner grounded delta, and high leg delta configurations. In an ungrounded delta system, none of the phase conductors are intentionally connected to ground. While this might seem counterintuitive, an ungrounded system can actually continue to operate even with a single ground fault, as there is no return path for fault current to flow. However, this also means that the voltage to ground on the unfaulted phases will rise to the phase-to-phase voltage, which can stress insulation and increase the risk of a second ground fault, which would then result in a short circuit. Furthermore, ungrounded systems can experience transient overvoltages due to resonant phenomena. To mitigate these risks, it is common practice to use ground detectors or ground fault indicators in ungrounded delta systems, which provide an alarm when a ground fault occurs, allowing for the system to be shut down and the fault located and repaired before a second fault occurs. A corner grounded delta system involves grounding one of the phase conductors of the delta. This effectively makes the grounded phase the neutral point of the system. Corner grounding provides a definite ground reference, limiting the voltage to ground on the ungrounded phases to the phase-to-phase voltage. It provides a simple and economical grounding method. This type of grounding can offer good protection against transient overvoltages and simplifies ground fault detection. A high-leg delta system, also known as a red-leg delta, stinger-leg delta, or wild-leg delta, is a hybrid configuration that combines aspects of both delta and Y systems. It is created by grounding the midpoint of one of the delta windings. This creates a neutral point that can be used to supply single-phase loads at 120 volts from two of the phase conductors, while still providing three-phase power from the three delta conductors. The voltage from the neutral to the third phase conductor, the high leg, is higher than the other two phases, typically around 208 volts, hence the name. This configuration is commonly used in older installations, particularly in rural areas, where it provides both three-phase power for machinery and single-phase power for lighting and receptacles. The specific requirements for grounding delta systems are addressed in the electrical code, focusing on ensuring personnel safety and minimizing the risk of electrical shock. The code details requirements for grounding electrode systems, which are used to connect the system neutral or grounded phase to the earth. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal underground water pipes. The size and type of grounding electrode required depends on the size of the service and the type of grounding system. The code also specifies requirements for grounding conductors, which are used to connect equipment enclosures and other metal parts to the grounding system. The size of the grounding conductor must be sufficient to safely carry the maximum ground fault current that could occur. The code also addresses the bonding of metal parts to ensure that they are all at the same potential, minimizing the risk of electric shock. Bonding conductors are used to connect metal enclosures, raceways, and other metal parts to the grounding system. The size of the bonding conductor must be sufficient to carry the maximum fault current that could occur. Ground fault protection is another important aspect of grounding delta systems. Ground fault protection devices, such as ground fault circuit interrupters (GFCIs) and ground fault relays, are used to detect ground faults and automatically disconnect the power supply. GFCIs are typically used in residential and commercial applications to protect against shock hazards, while ground fault relays are used in industrial applications to protect equipment from damage. The electrical code provides specific requirements for ground fault protection, including the types of devices that are required, the locations where they must be installed, and the performance characteristics of the devices. The selection of the appropriate grounding method for a delta system depends on several factors, including the type of loads being served, the size of the system, and the desired level of protection. Ungrounded delta systems are typically used in applications where continuity of service is critical, as they can continue to operate even with a single ground fault. Corner-grounded delta systems are often used in industrial applications where a simple and economical grounding method is desired. High-leg delta systems are commonly used in older installations where both three-phase and single-phase power are required. In any case, it is important to consult the electrical code and a qualified electrical engineer to ensure that the grounding system is properly designed and installed. The code does not specify a specific amperage threshold that mandates the installation of a delta ground. Rather, the requirements for grounding depend on the specific characteristics of the system and the loads being served. However, the code does provide general guidelines for grounding systems, which must be followed regardless of the amperage of the service. These guidelines cover topics such as grounding electrode systems, grounding conductors, bonding, and ground fault protection. It's essential to consult the latest version of the electrical code and seek guidance from a qualified electrical professional to ensure compliance and safety in any electrical installation involving delta systems. The lack of specific amperage-based requirements for delta grounding in the provided text highlights the importance of understanding the general principles of grounding and bonding, as well as the specific requirements for different types of systems. By following these guidelines, electrical professionals can ensure that delta systems are properly grounded and protected, minimizing the risk of electrical shock and equipment damage. The absence of a specific amperage threshold for delta grounding underscores the need for a holistic approach to electrical safety, where all aspects of the system are carefully considered and designed to meet the requirements of the electrical code. Firstly, grounding ensures a low impedance path for fault currents to return to the source, allowing overcurrent protective devices like circuit breakers or fuses to quickly trip and energize the faulted circuit. This minimizes the duration of the fault and reduces the risk of electrical shock or fire. Secondly, bonding ensures that all metal parts of an electrical system are at the same potential, preventing dangerous voltage differences from developing between them. This is particularly important in areas where people may come into contact with metal surfaces, such as enclosures, raceways, and equipment housings. Thirdly, ground fault protection provides an additional layer of safety by detecting and interrupting ground faults that may not be large enough to trip a standard overcurrent protective device. Ground fault protection is typically required in services and feeders rated 1000 amps or more, but it can also be used in smaller systems to provide enhanced protection. Understanding these fundamental principles is essential for designing and installing safe and reliable electrical systems regardless of the type of system or the amperage of the service.